So for example 3, you're going to need to use your calculator because I think you'll notice it's asking here for a regression equation. So we're going to be using the calculator for that. And it wants us to find specifically the logistic regression equation. So we'll go ahead and do that, and we'll begin by entering the data into our stat list. So you go to, let me quit, sorry. You want to go to stat and then edit. You may remember we did this before. Ideally, we like using L1, L2 because that's the default for X and Y. So I'm just going to go ahead and do that. And I'm going to use 0 for 1950 because it told me to, and then so on. So 1950 would be 0, and then 1960 would be 10, 1970 would be 20, and so on and so forth. And then the corresponding populations in millions are 2.8, 5, 6.8, 9.7, and 12.9. Okay, so it wants us to find the logistic equation and then superimpose that onto the graph. So first I'll just calculate the equation. So if you scroll down here, you'll notice, I think it's like the last one, or one of the last ones, you'll see this logistic. That's the one we want. So we'll hit enter. Now because I use L1 and L2, I can just hit enter again. If you use a different list, you'd have to type that in. Okay, so you'll notice that this is matching this same equation. It's matching this same equation here. Just uses different variables. So now that we're in AP Calc, we have to be comfortable with switching variables and renaming them because it happens all the time. Okay, so I'm going to go ahead and just fill everything in. So for part A, I got y equals, and if you'll notice, it's got C in the numerator, and C is 24.762. So 24.762 divided by, and then it says 1 plus A being 7.195. So 1 plus A times E, which is the base of E, which is 2.7, whatever, to the power negative bx, where b is the 0.051 and x is the variable. Oh, sorry, negative. So it's negative 0.051x. Okay, so that's the answer to part A. Then it wants us to superimpose the graph on a scatter plot, so let's go ahead and do that. So we'll go ahead and turn the scatter plot on, but make sure, okay, yeah, so I've got L1 and L2, so I'll just go ahead and do, oh wait, let me delete these. This must have been from the slope field. Okay, so there's plot 1, and I want to change my window. Oh yeah, I don't like these either. So my x's, if you recall, are going from 0 to like, let's go from say 0 to 100. And maybe we'll just go every 5 years. And then the y values are going from 2.8 to 12.9. So I don't know, maybe like negative 1 to 15. And then just go by ones. Okay, let's take a look at the scatter plot. So there's our scatter plot. Now they want us to copy this equation on there. So that's where you go back to the y equals. And we want to copy the equation there. So to copy the equation, we hit this button vars. And we're trying to copy down one of our stat equations. So we go down to 5. And we're copying down a regression equation. So we arrow over to equation, and then there it is, regression. And then it copies it. Now I know some of your calculators have an issue with this. So what you can do, so I'm going to do or, I'll show you. When you're going to calculate your equation, you can go stat calc, go down to logistic, and you can go, so we're going to do, I think, gosh, how did this work? Let me try this. I'm not sure if this works, but let's see. So what I did is I entered logistic and then I did vars y1. And what I think that will do is it'll calculate the equation for you and also copy it into y1 for you. So there's the same equation as before. And then, yeah, okay. So when you do that, it calculates the equation and copies it into y1. And so now it'll overlay the graph onto our scatter plot. Eventually. Is it not selected or something? Okay. Okay, that's odd. Oh, okay. So, okay, I'm not quite sure what, maybe because it's increasing so fast. Maybe I'll decrease this down to 50. Let's see if that helps. There we go. I think I went too far to the right, and so it was increasing so fast it didn't show. Sorry about that. So that's 0 to 50. Okay, so it looks like it's just a regular exponential graph. So we went over to 50 here, and then I think I was up to like 15. And then it's going to cross through the y-axis. It looks like, here, I'm going to go ahead and see what happens when x is 0. Okay, so it's crossing through the y-axis at about 3. And then it looks like it's just kind of going up. But I want to warn you, it is going to cap off at some point. So I need you to notice something. This is super important. So I'm going to show you this in red. It's not going to go up forever. Let's take the limit as x approaches infinity, which is going on forever, of this function, of the 24.762 divided by 1 plus 7.195 e to the negative 0.051x. Okay, we're going to let x grow without bound. And remember, e to the negative is like 1 divided by e to the power. So this is going to turn into a really large negative. And so it's going to become 1 divided by a really large negative. So it's like this. And x is growing indefinitely. So this is going to be a small number, 7-ish, divided by a gigantic number. That is going to tend off towards 0. As x gets really large, it will. As x gets really large, this portion of the equation is going to approach 0, leaving 24.762 divided by 1. So it looks like this function has a limit. It cannot get any bigger than that. Even x is going off to infinity, it caps off. So what I want us to do is take another look at this curve. Let's go to our window. Let's increase the y value to go beyond that limit. So let's have it go maybe to 26. And let's take another look at the direction of this curve. So right now it still looks like an exponential graph. So this is where I'll take the x's out a little further. Maybe now I'll have x go toward 100. And you can see the function begins to level off. Let's go a little bit higher for the y values. And maybe a little further for the x values. So you can really see what a logistic equation really looks like. That's actually what the function's doing. Let's go ahead and put in the 24.762. And you can see it's a horizontal asymptote for the function. So this is just sort of a little review. When you're finding a limit as x approaches infinity, if that limit exists, that's the horizontal asymptote, meaning the cutoff point for that function. So this is equal to the horizontal asymptote, which is none other than the carrying capacity. And if you compare this setup with the equation that we solved for, you see that the m, which was the carrying capacity, always ends up being the numerator of a logistic equation because it always ends up being the horizontal asymptote. So if you're given the equation in this form and asked to find the carrying capacity, it's pretty much going to be whatever number's in the numerator. Okay, so now that you've seen this, we need to adjust our graph. Let's go ahead and make that 25. We realize our cutoff is going to be somewhere around there. Well, somewhere below there. Let me go a little bit below there. Be just below there, and we know that it's going to kind of go, and actually let's kind of see roughly where it begins to change. So let me go ahead and hit my trace real quick. There we go. And it looks like it changes right around 48, 49 years or so. It's like right here. So it's going up, 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 up till it hits there, and then it begins to taper off because it is never going to get any more than that. So that is a more accurate graph for part A. So be careful when you're doing these problems. Whatever is in your numerator, you want to make sure your window goes at least as high as that so you can see the behavior, the true behavior of the function. Okay, then for part B, it says find the carrying capacity. We already did that. It's 24.762. For C, it says find the rate of growth. Sorry, find when. So we're going to be solving for T. Find when the rate of growth changes from increasing to decreasing. Okay, the rate of growth is the derivative. Anytime you see that word rate, that's the dp dt. So let's go ahead and go back to our calculator. So we're going to do this all in the calc because it's going to be really scary if we didn't. Okay, so we're going to go back to the calc, back to my y equals. I think I'll turn my plot off. I don't really need it at this point. And what I'm going to do is calculate the derivative of y1 by using my n-derive and using my vars, y1, comma, x, comma, x. And I don't want to look at the graph of y1 because it'll get in the way. I want to just look at the derivative and see when the derivative changes. I want to see when the derivative changes from increasing to decreasing. Okay, so I'm going to go ahead and graph the derivative. And it's like barely crawling way down here. So we're going to need to adjust our window. Looks like our derivative is really small values. And right now I have really large values. So let's go to my window. Let's back this back up to 50. I mean, not 0, just kidding. 50, and then we'll have the y max be 10. Let's try that. Okay, still looks pretty low. So we're going to make the y max even smaller than that. So because it's hard to tell when it's increasing, when it's decreasing. It looks like a flat line right now because the values are so little. So, okay, let me go back. Maybe I'll have this go all the way down to 3. Okay, so now we can see it's increasing, still increasing. It's going up. So this is, again, this is the derivative. This right here is the rate of growth. Okay, let's go a little further. Yeah, let's do that. So it's increasing, increasing, increasing. One of these, there it goes, okay. Okay, so somewhere in this long stretch of time, it changed from increasing to decreasing. So let's go ahead and do second calc max. Because the maximum is when a function changes from increasing to decreasing. So I'm going to back it up. Oh, gosh, sometime in the near future here. All the way over to where it goes down, okay? And then go back to the right. All the way over to when it goes down. And then we'll figure out that part. And down, hit enter, and then somewhere in there is where it hits the max, which is where it changes from increasing to decreasing, and that is when x is 38.44 or 38.445, and that's in years. So t is 38.445 years. It also wants us to estimate the population at that time. Now that's P of t. So P of 38.445. Well, fortunately, I still have that in my Y1. I never got rid of it, thankfully. So I could just do, I could just do Y1 of 38.445. Because the equation in Y1 is the equation of population at a given time. So here's the given time. Plug that in for T. And the population is about 12.38 million. Because the original equation was given in millions. Whew. Okay. So that was a heavy use of the calculator there. That was example 3. And then last one is example 4. So suppose you decide to estimate the population in Florida to be 16 million in the year 2020. Include this data point with the data in example 3. So it's saying add it to this. And then find the new logistic equation and the new carrying capacity. Okay, so that's not going to be so bad. So we're going to go to stat edit. And I'm going to go ahead and add in the year 2020, which would be 70 years after 1950, so that would be 70, because zero represented 1950. And then they're saying let the population be 16 million. So there we go. So I'm going to calculate that new equation with that new data point, see how it changes it. Okay. So here's my new equation. And I'll just copy everything down to the third decimal place. So I'll get y equals c in the numerator, which is this number to the third decimal place. So that's 16.899 divided by 1 plus a, which was the 5.132, times e to the negative bx. And b was 0.0666, so 0.067 x. And that's it for part A. And then for part B, we learned back in example 3 that the carrying capacity is basically the numerator of the logistic equation. So it's 16.899 million. So now if you add this new data point into the mix, look how much it changes how much the environment can hold. So now it can only hold up to 16.899 million versus 24.762 million. And that is all for 6.5. Come see me in tutorial if you have questions, and I will see you in class.